All right. Hello, everybody, and welcome to Technically Speaking. This is episode 9, Substructure Mastery, where we're going to take a lot of what we've been discussing here for the last several months through 2022 and begin applying those concepts specifically to a part of the structure that sometimes gets overlooked, actually, and many times gets misunderstood, and that's the substructure. So again, welcome for joining us here. Just a couple real quick housekeeping items. First and foremost, remember that we don't use the chat feature during the Technically Speaking episodes. We use the Q&A feature. So you'll find that Q&A feature probably in your top ribbon there with Zoom. And anytime during the presentation today, if you have a question, just open up that Q&A, drop the question in there, and I'll address all of those questions at the end of the session. So make sure you drop those in there so you don't lose them. And with that, let's go ahead and get started. Again, this is episode 9, the 9th month of the year. We've been running one of these every month. And we have a few left here for this year. My name is Brandon Burton, and I am the Senior Principal of Industry Relations here at CoreLogic. I'm also the chair of the ANSI ICRC standards, and a lot of the content that I bring you in Technically Speaking is really coming from that vantage point as an industry activist and as a standards participant and volunteer. So with that, let's jump right into it and get started. The first piece I want to talk about for just a moment today, some of you will recognize, if you were in some of the earlier sessions this year, you'll recognize this graphic. This is one in one of the very recent episodes where we talked about interstitial cavities and voids, like wall cavities and attics and crawl spaces, et cetera. And we really highlighted the fact that 42% of the overall structure that we're dealing with, depending on the size of the building, but approximately 42% is some form of inaccessible or typically non-visible space within the building. And I think a lot of times as drying contractors, to kind of set up the substructure conversation, we spend a lot of our time focusing on what we can see in the building and monitoring what we can see and installing drying equipment for what we can see, and we overlook the stuff that we can't see. We spent a lot of time back on episode 7 talking about that with the interstitial spaces. So if you missed that, I'd really encourage that you go back and look at that, especially if you deal with a lot of hardwood floors, cabinets, wall cavities, and these types of things. So today's session is kind of an extension of that. We're going to take that same kind of line of thought here, and we're going to move into substructures. And substructures can include a couple of different spaces. They can be basements, finished or unfinished. They can be crawl spaces, really any area that is beneath the main floor living space of a structure. These spaces are unique in terms of the way we approach them for drying. They're typically unique in the nature of construction and the types of building materials that we encounter. They present unique challenges for access to outdoor air and ventilation as appropriate. So lots of unique challenges they bring that we want to unpack today. As we go there, I've got to start with a little safety meeting, of course. Always begin every conversation with a quick touch on safety. Some of these spaces are technically what we would define as a confined space. And I'm not going to get into OSHA and regulation and all of that. I just want to ensure that you have awareness that when we are dealing with a substructure or really any space within a structure that is not intended for occupancy, that has limited ingress and egress. In other words, it's not real easy to get in, it's not real easy to get out. That generally these spaces are what we call permit required spaces. And a lot of people misinterpret what that means, what a permit required space is. But generally what that means is that somebody other than you needs to know that you're there. Needs to know when you've gone into the space, when you plan to come out of the space, and you need to report to that person that you are entering the space and then leaving that space. You also need to post that you're in that space. And that's kind of a really loose general description of the way we manage confined space. And there can be even more considerations depending on what's in that confined space. So just be aware of that if you frequent crawl spaces, for example, this is something you at least want to be aware of and at least do a little bit of research on some of the really basic and actually quite simple steps that you can take just to make sure you're safe. And of course, wear the personal protection that's adequate for the area. The most commonly overlooked piece of personal protection in a crawl space, for example, is a hard hat. I spent a lot of time in crawl spaces and can tell you the first few times I went down without a hard hat, I typically came out without my head feeling real great for a while. So wear the appropriate personal protection. So safety meeting adjourned, we can check that off the list. A couple of different areas here again for confined space that I want to dive into today. On the left-hand side, we see a basement, right? And this could be an unfinished basement. It could be a finished basement. But by basement, generally what I'm describing is I'm describing an area that is mostly or partially below grade. So you can see there in kind of the gray shaded area that we have the grade of the outdoor environment. So that's the level of the ground. And we have a portion of the structure that is below that upper level of the ground or below grade. This creates a lot of unique challenges simply and really just predominantly because of the fact that we're dealing with a below grade structure. We're dealing generally with a very, very different range of temperatures across the building materials that are in contact with the outdoor environment that'll not be typical of what we're seeing in the living space up above. And in addition to that, those building materials themselves are also generally going to be different. The nature of that construction, obviously below grade, is typically very different than structure that is built above grade. That presents some unique challenges for how we approach the monitoring process, how we investigate water migration, how we facilitate drying, and even the psychrometric analysis that we're going to make of that environment. So we'll come to that more here in just a second. On the right-hand side, we have what we would call a crawl space. So this isn't an occupied space. This is a stick-built structure that is built upon, some sort of a footing that it elevates it above the ground. And we have a space that is now beneath this structure, which is probably ventilated to the outdoor environment, not always. It depends upon exactly how that's constructed, but most commonly, it is constructed in such a manner that it is ventilated to the outdoor space. So we're going to talk a little bit about the basement and finished and unfinished. We're going to talk a little bit about crawl spaces. But as we drill into that, the first thing I want to touch on is the psychrometric portion of confined space drying. There is a very specific way in which I'm going to suggest that you set your target drying conditions in a confined space, not a confined space, but a substructure, excuse me. And typically, when we're dealing with a living structure, we have the luxury of having a better understanding of what we're dealing with in terms of the psychrometric environment than we do with a substructure. And there's lots of reasons for that, and I'll touch on some of those. But because of those reasons, I'm going to bring back a concept that we talked about a couple of episodes ago regarding dew point temperature to help you really grapple with how do I know whether or not my below grade space has adequate drying conditions, and a way that you can set this target really, really simply and ensure that you're providing an adequate drying environment in that substructure. So it's all based on dew point. The general information I'm going to cover here is outlined in these 3 bullets, but let's dive into each of these 3 bullets and talk about them in more detail. By the way, what I'm covering here, if you want to go even deeper into this conversation, go back to episode 8, which was just last month that we went through in episode 8, and we talked more about this concept in a different application. So first of all, the one thing that you need to understand about dew point temperature is that dew point temperature is the temperature at which an air mass is at risk of not supporting evaporation, but the opposite. We begin to have the risk of supporting condensation, where an air mass is not going to dry a surface, but potentially physically wet the surface by depositing moisture on that surface. It does that because that cold surface is taking energy out of the air, right? And energy is what is required to support that water vapor, if you will, in really, really loose terminology. The concept that we talked about back in episode 8 was that a good drying condition is one where the dew point temperature of the air you're using, right? So this is the air that's being circulated through the space. That dew point temperature is 20 degrees below the surface that you're putting that air in contact with. What that does is it creates a gradient or a delta that gives the air enough energy and capacity to support transport of additional moisture. So what does all that mean? Because that sounds really, really complicated. Well, it really isn't. And in order to understand that, let's take a look at the psychrometric chart here for a second. First, dew point temperature is generally a scale all the way over on the right-hand side. I have it highlighted in blue here to call it out. And those numbers that you see there on that dew point scale are temperature. All right, and we're looking at a chart that is in Fahrenheit. So it's imperial measurements here. So down at the bottom of that scale, you see 10 degrees Fahrenheit. Near the top of the scale, at least the last number you see is 80, and of course it keeps going up from there. So what does that mean, and how do I apply that? The first thing you're going to do is you're going to go into the space that you're drawing, the basement, the crawl space, and you're going to consider, where do I think my coolest temperatures are going to be along my affected surfaces? Where this water has come into contact or directly or indirectly affected building materials, where do I think it's going to be coolest? And a little bit of logic can typically help you identify that area. But the reason this is important in a substructure is you can't just rely upon your indoor and outdoor temperatures to have an understanding of what temperatures you're dealing with, right? It could be 80 degrees outside, it could be 70 degrees in the living space, but that doesn't mean that your surfaces in a below grade space are going to be between 70 and 80 degrees, right? It could very easily be significantly lower than that. So it's really, really important to step back and make this consideration when we're dealing with below grade spaces. So where is that coolest temperature going to be? Typically, it's going to be where you have the most building material in contact with the deepest and most exterior grade around the structure. So an example may be here in this area where the slab has come into contact with the footing wall, and that area is likely to be one of the cooler areas that you're going to be encountering within the space. So consider that temperature. Get a little laser thermometer, shoot a temperature of it, get a feel for what that temperature is going to be, and then plot that temperature on your psychrometric chart. Now notice here in blue, I've got that temperature. Let's say that temperature is approximately 60 degrees. And I've identified that I think that's probably the coldest any of my affected materials are going to be, so around 60 degrees. And I've plotted that in blue on the psychrometric chart. The next thing you're going to plot on the chart is the 20-degree delta dew point. So here I've got 40-degree dew point, and I've plotted that in yellow, okay? Notice where those two intersect on the chart, all right? And this is the reason why this concept works, by the way. Regardless of what my drying air is in the building, as long as I keep that air drier than that yellow line, I don't allow my grains of water vapor to be any higher than that yellow line, which incidentally is approximately 38 grains on this chart. If I never allow the moisture content in my air to be higher than that, then the relative humidity on the cold surface will never be above normal. Notice how that works, that 20-degree dew point delta. The two green dotted lines are the relative humidities of 40 and 50%, the normal indoor range, okay? As long as I use this concept, even at the coldest point, when air moves to a cooler surface and relative humidity climbs because the air is cooling down, that relative humidity will never exceed 40 to 50% relative, which means that air will be sufficient, even at that temperature, to allow the material to dry back to a normal moisture level. I can achieve my drying goals as long as I've got this 20-degree dew point delta, okay? And I know that's it's a mouthful, it's a mindful to kind of swallow that concept. To back that all the way out, again, the simple is just ensure you understand where are my coolest affected materials, the materials that will potentially be the coldest within this drying environment. What is that temperature? Plot that on the chart, plot your dew point at 20 degrees below that, and find out where they cross on the chart. What you just established is that this environment should not have a humidity greater than approximately 38 grains per pound. That's your target. That particular substructure should be no wetter than 38 grains for your drying environment. It's really important to grasp that concept. And I know technically, if you've never really thought about psychrometry in this way or thought about a drying system in this way, it can kind of hurt the brain a little bit to think about it this way for the first time. It's kind of like going to the gym. And if you haven't done a lat pull in a long time and you go to hit the lat pull for a while, you're going to feel it for a while. It's going to hurt, right? Well, the brain's just a muscle. And if you haven't thought about your psychrometrics this way, it's going to hurt a little bit the first time you think about it. But if you listen back to what I just described a couple of times, grab a psychrometric chart and plot that a couple of times on a psychrometric chart, it'll make sense. Not only will it make sense, you'll start to think psychrometrically and accurately about how to set these drying goals within these substructures. So again, the simple P equals, P being target temperature, equals the surface temperature minus 20. That's my dew point, minus 20. How many grains per pound do we have at that condition? 38. Be below 38 grains, and you've got a healthy drying environment. Provided, of course, you've got appropriate circulation and everything else. So So anyway, this is using dew point temperature to establish an appropriate drying condition. Now, once I introduce my drying condition, hopefully we're going to be a little warmer than 60 degrees on most surfaces. Notice what happens here with that condition. So most of my surfaces, if I bring in air and maintain a temperature of 80 degrees, now most of them are going to see air at 80 degrees and about 22% relative humidity. You're going to have a lot of really good drying on a lot of those locations. And hopefully that 80-degree air brings the temperature of that 60-degree surface up a bit. Really difficult to do, though, when you're talking about a whole bunch of cement or concrete and exterior dirt up against the exterior of that concrete. That's a big heat sink. And expecting everything in that basement or other substructure to achieve that same temperature as your air is very, very unrealistic. And that's the reason why you have to consider, again, what is that coldest temperature that I'm going to be dealing with on a surface, and how do I get my dew point of my air to at least 20 degrees below that. Okay. All right, so that's using dew point. And again, this is my reminder for you that if you haven't yet, start dropping some questions over into the Q&A area at the end of the session today for those of you that are with us live, because we do record these. But if you're with us live, I'll go through all of the questions that you drop into the Q&A at the end. So I haven't seen any questions dropped in there yet, so please make sure you're dropping those in there. So now let's get into the setup. All right, so now that we understand a little bit about the goal, right, the psychrometric goal and the target condition that we want to achieve, let's talk a little bit about how we might set out to achieve that goal, depending upon the type of substructure that we're dealing with. So what does the equipment setup look like? All right, so again, we've got two different types of substructures here. On the left-hand side, we've got your typical basement, which may be finished or unfinished. On the right-hand side, we have the crawl space. Generally with through basements where we are fully below grade, or at least below grade to the point that I wouldn't call it a daylight basement, we're dealing with a few limitations that are unique, where a crawl space, believe it or not, would actually be easier than the basement would be. First of all, you're dealing with a lot more depth into below grade, right? Dealing with a lot more concrete. You're dealing with a lot more materials that are dense, that are difficult in releasing moisture. You're also lacking the ability to really establish any ventilation with the outdoor air. And generally with substructures, I really try to leverage outdoor air ventilation whenever possible for lots of reasons, and we'll get into those. But in a true below grade basement, that can be quite difficult. So in many cases with a true below grade basement, your equipment setup is going to look very, very typical to your normal installation in an above grade structure. You're going to use circulation of affected air, you're going to use mechanical dehumidification, but you're going to add to that mix that metric of having your indoor condition have that 20-degree dew point delta, right? That's still going to be uber critical to ensure that you understand that on that basement with the cement underneath that carpet, if it's finished or whatever else, if that's 60 degrees, right, then I can't have air that's any wetter than 38 grains. If it's any wetter than 38 grains, then that cement is not going to dry effectively, right? If I'm at 60 or 70 grains per pound, that's going to translate to a relative humidity at 60 degrees of about 80% RH. That cement is only going to give up moisture until it acclimates to that 80% RH, and that's not going to get you there, right? That's not going to get to the finish line. So it's really important to add in that means of establishing that delta. And what that may drive you to is the type of mechanical dehumidification that you're using. It may very well alter that scheme. At a very minimum, in a basement area with lots of cement, we should be dealing with low grain refrigerants, right? And we've talked a bit about dehumidifier technology in a previous episode. The other technology that we may dive into in this case would be desiccants. If it's necessary to get me down to 38 grains and your low grain refrigerants just aren't doing it, then we may want to drive down to a desiccant dehumidifier. You may also consider running your temperature in that basement a little bit lower, right? If your temperatures are 90, 95 degrees because of your drying equipment within that space, then you may actually need to bring the temperature down slightly, because that may be the reason why you can't get the grains low enough, especially using refrigerant dehumidifiers. In a future episode, we'll talk about refrigerant limits, but the warmer the air is in that space, the more difficult it is for a refrigerant to lower the grains. I like warm air for supporting evaporation, but it does the opposite thing to my dehumidifiers. The warmer that air is, the more difficult it is for them to create low humidity. And in an above ground space where my temperatures are more evenly affecting the environment, that's not a significant limiter as it is where I'm dealing with a lot of heat sinks with materials that are very difficult to warm up, right? All right, so on the crawl space side, generally, I'm going to consider using an open air exchange equipment setup. However, there's lots of things I've got to think about first. Regardless of my setup, I'm still going to target that 20-degree dew point delta, right? I'm still going to target that. And if my considerations don't give me a positive answer, I'm still going to use a traditional closed system in that crawl space. I just don't like to do that because of the limitations a crawl space presents. There are several of them, not the least of which being just getting the equipment into the space, right? Fortunately, today we have dehumidifiers that are of a profile that's a little bit easier to get them into most crawl spaces, but I've definitely been in a few where even some of your lower profile dehumidifiers are going to be really difficult to get into that space and maneuver within that environment. So I like to avoid it if I can, but here are the questions that I ask to determine if I can use an outdoor air exchange. First of all, I need to think about that outdoor air. Will the moisture level in the outside air support that 20-degree dew point delta? All right, so take a look at your outdoor air, and I'm not talking about its temperature or its relative humidity. I'm talking about grains. How many grains per pound are there outside? And what is the dew point of that air outside? Will the dew point of that air be 20 degrees lower than the cooler surfaces I'm dealing with in this below grade structure? And for some of you, yes, it's going to happen that way a lot. For some of you, no, it's probably never going to happen that way. Fortunately, for those of you that deal with more humid outdoor air, crawl spaces aren't as common, right? For exactly that reason, actually. But for those of you that live in northern climates, we see a lot more crawl spaces, especially northwestern climates, then these crawl spaces typically are going to be afforded well for most of the year with an outdoor air ventilation when you ask that question. The next thing I need to ask, let's say that the outdoor air can support ventilation. The next question I need to ask is, can I securely access that outdoor air, right? Can I do so securely? Is there ventilation? Can I use vents? Is there an access area? Can I use that access area? If it's an exterior access, that's bonus because it's a little bit easier to use that access for equipment setup than it would be an interior access. So all of those questions, how do I access the air in the space and out of the space? How do I make those two commune, right? And is there a way to do that securely? And then last but not least, if that's a yes, and I can accomplish that, then I start asking myself about the stability of outdoor weather, right? Just because it's a good, favorable condition right now doesn't mean it's going to be in 24 hours. Just ask the folks in Western Central Florida right now how quick weather is going to change, right? So it's really important to ensure you understand the weather patterns that are around you that time of year. Are there any systems that are moving in or around you that are going to significantly change the weather? And does that change your determination about that 20-degree dew point delta? Right. Now, again, for me, at least for the area that I've spent most of my career operating, most of the time with crawl spaces, this is going to give me a favorable result. And I will use an open air exchange system. If not, then I'm stuck with the traditional closed system. Okay. So use dew point 20-degree delta kind of in review. Traditional closed system, if the outdoor air, circulation, ventilation, et cetera, aren't going to work for you. And again, that 20-degree dew point delta being one of the most critical things that you're going to consider, because that is the target. Okay. All right. So once I've considered all of that, let's talk about the setup. Generally speaking, the most effective setup for an exchange system is going to be one where I have some form of temperature control over the outdoor air being brought into the space. By temperature control, what I mean is that generally when we're dealing with outdoor air that is dry enough to support the process, it's generally true because it's also slightly cool or maybe significantly cold, depending on the time of year. So generally we'll need some sort of temperature control to ensure that that air is not only dry coming into the space, but also warm enough to support drying. This is generally done with one of a number of systems. Usually the most efficient is going to be something like an indirect fired portable furnace system. Generally, the most effective way to provide the amount of heat that you need there without significant electrical concerns is to use something that is fired, but also something that is indirect fired, meaning we're not putting the byproducts of the combustion directly into the airstream, right? Set up on something like this, pay attention to your owner's manual, make sure you understand how to manage the exhaust of a system like this and how to operate it safely. However, never bring air by force into a substructure like a crawl space without an equal or greater ventilation on the opposite side. I don't want to positively pressurize this space. I don't want to put, 2,000 cubic feet of air per minute into this space and just let that build a positive pressure, because I don't want everything that's in this crawl space being forced through exfiltration up into the living space above. So I have to remove an equal or greater, and most likely greater, amount of air from the opposite end. And this is really important from an engineering control standpoint, not only that you're removing more air so that you become negatively pressurized, so we don't force any of the contaminants out of this space, including but not limited to moisture, but also so that we ensure that the air circulates through the space effectively. In fact, depending upon the complexity of this environment, you may actually want to use multiple exhaust points so that you draw air to the extremities of the different areas of the space that you're trying to dry. So sitting down and really thinking logically and kind of drawing out a floor plan. What does this look like? What is my greatest distance from one end to the other? And that's kind of your cross flow that you want to create. But where are the extremities that may not get the circulation? Do I also need to exhaust there to draw my drier air out into those corners and those extremities? Really think through that logic. All right, really think through that logic. And once you have the system installed, start checking your exhausts, all of your exhaust points with a thermal hygrometer, and ensuring that you've got warm air exhausting at all of those points. If I'm bringing in air, at a warm temperature from outside, and I've got a warm exhaust here, but over there's a cold exhaust, I'm not getting the circulation that we're looking for. And also, even though it's not fun to do, spend some time crawling around in the space and validating an even condition throughout that environment, at least in the areas affected. All right. Here's the next note I want to give you on dealing with crawl spaces that I think often gets misunderstood and overlooked. The purpose in drying a crawl space is to dry the structure. All right, it's not to dry the dirt. And I'm gonna say that a couple of times because I know this is one where some of us could probably argue back and forth in a couple of different directions. But the purpose of drying a substructure is to dry the structure, not to dry the dirt. So my suggestion to you on this is that at least initially, when you've got massive amounts of standing water, you've got wet insulation that has fallen down out of the floor, and that's just soaping wet on top of the existing vapor barrier, if it's even there, that you remove that vapor barrier, you remove that damaged insulation, or insulation rather, if necessary, pump out bulk water, and then begin your ventilation and begin the drying process with the vapor barrier removed until you get to the point where the surface of the earth in that crawl space isn't mud, right? You're not slopping through mud to get through the crawl space. And when you've gotten to that point where it's still damp, it's still wet, the ground is still wet, but it's not muddy, reinstall the vapor barrier. And at that point, let the dirt finish dealing with the dirt and focus on the structure. It is not necessary to dry dirt to a dry standard, okay? It is necessary to dry joists to a dry standard, posts to a dry standard, sill plates and mud plates to a dry standard. It is not necessary to dry dirt to a dry standard. Now, notwithstanding the fact that you have to understand, what was the source and has the source been properly addressed, et cetera? Are there contaminants that also needed to be dealt with because of the source of water? So a slightly different conversation, we bring some of those into the mix, but generally speaking, the purpose is for drying the structure. I noticed a couple of questions popped in as I was talking through that. So again, just a reminder, please, if you have any questions as we're going through this material, make sure you drop those into the Q&A. So we're going to hit those right after we finish up our presentation today. All right, so that's the equipment setup. The next area here that I want to take a stop on is going to be the math. All right, so how do I evaluate the effectiveness of my drying systems when I'm dealing with substructures? What does that look like? And this is another one where we get an opportunity to take a look back at an earlier episode. In episode 8, again here, we dealt pretty deeply with the math associated with air exchange drying systems and how to validate the effectiveness of an air exchange drying system. So this is just a quick reminder of some of the content that was in that episode, where we took a look at the grain depression, right? And that's the difference of the moisture in the air going into a system versus the moisture in the air leaving the system. In this case, the system is a substructure, right? So what is the humidity or grains of the air going in from outside if I'm using open exchange? And then as that air moves through the space, it's going to pick up some moisture like a sponge. What is the grains per pound now leaving that space? The delta, the difference between those two, we'll call that a grain depression, even though it's a grain rise. We'll call it a grain depression. So that grain depression times the volume you're doing it at, the CFM, and then, minutes in an hour, hours in a day, grains in a pound, weight to a gallon, et cetera. We can do some math with that and turn it into pints. What we learned to do in that episode was to simplify minutes and hours, et cetera, into a single number. And what we learned to calculate was grain depression times CFM divided by 71 is pints per day, right? So if I've got an environment where I'm bringing in 27 grains from outside, as you see in the example here, and then I'm exhausting 105 grains from the space by the time I'm done, that grain change is 78. I'm picking up 78 grains on the way through. Multiply that by your CFM rate, divide by 71, and we find out that's 110 pints per day. I know math makes a lot of us go cross-eyed and sideways and and tune out, right? But just think for just a moment how important this is. If I've got a dehumidifier and it's pumping out water, homeowner, property owner, whomever it is, property manager, they see it pumping out water, they go, it's working. Right? It's really easy to understand the value, the importance of a dehumidifier. And even the fact that you're still drying, right? Even though technically that's not really what tells me if I still need to dry, to the layman, when they see water still pumping out of a dehumidifier, I think they kind of understand that, there's still water inside the building, right? In reality, there'll be water pumping out of the dehumidifier until the end of time, right? But at least they get a visual from that. When you have a heating system or just a ventilation system installed on a crawl space or a daylight basement, and a ventilation system on the other side, they don't have that layman way to understand that progress is still being made, right? In fact, they've probably never even seen their crawl space, right? And even if it is still wet and muddy downstairs, if everything looks fine, smells fine, and acts fine upstairs, it can be really difficult for them to understand that progress is still being made and needs to be made. So if I can, instead of just having a ventilation system installed, if I can come up to somebody and say, you know what, we're still removing a significant amount of moisture from the crawl space. In fact, we're getting 110 pints of water per day out of the environment, right? That at least gives that layman layer, if you will, to the information to help them understand that it's a significant amount of water we're still removing. And by the way, this is an example with a very low CFM. Typically, your exchange rates will be 10 times that, right? So that's how we would do the math. We would use that grain depression mathematical calculation, grain depression times CFM divided by 71, right? Now would turn that into pints. That helps us understand the performance of the system. Now, secondarily, it's not just the performance of the system, it's are the materials still wet and are the materials still making progress? So monitoring in materials with substructures. Much of the monitoring in substructures is going to be the same typical monitoring that we would see with any other part of the structure, right? We're still going to be using non-invasive meters to scan certain areas, pin type meters to measure the things that are accessible with pin type meters, trying to find unaffected areas to establish dry standards and drying goals, et cetera. So most of that is all going to be the same, but there are going to be a couple of exceptions. The first is that we're dealing typically in substructures with a lot of concrete, especially in basements. We're dealing with a lot of concrete. And whether I'm a slab on grade or a slab below grade or footings below grade, monitoring concrete is a little more challenging than monitoring wood, right? So again, here in blowing the dust off a conversation that we had all the way back in March in episode 3, the most effective way as a restorer to evaluate the progress of concrete is to do what we call an ERH measurement, which stands for equilibrium relative humidity. And I'm just going to go through this relatively quickly, but generally this is done by using a hygrometer to evaluate the relative humidity in equilibrium at the surface of that material. And there's a couple of different ways to do it. Some are more accurate, some are less accurate, but this will at least give you an indication if you do it in the same way as you did the previous day. It'll at least give you an indication of rate of progress or direction of progress, right? So I'm not going to go through it in great detail. Again, if you want to review this, back in episode 3, we talked about this in great detail about how to go through the process of monitoring using equilibrium relative humidity, okay? What I do want to spend some time on today, though, is talking about how to extend your reach and being a little bit creative with invasive instrumentation within these spaces. Even in concrete, believe it or not, an invasive meter can be quite useful. It requires a little bit of destructive testing, right? We have to ensure that the pins can be inserted into preset holes. You're going to have to use an appropriate bit to create the hole to put your invasive instruments into. But once you have the invasive contact set, those contacts can be used for monitoring throughout the duration of the entire process. This is not only true for cement, it's also true for very thick structural wood. If we're talking about posts and beams and other materials that are typically much thicker than the range of your standard instrumentation, then the invasive meter can be used with appropriate fasteners and drill bits or other metal electrodes in order to access deeper into those building materials. And then those electrodes can be left in place throughout the duration of the drying process, and we can re-inspect at that same exact location over and over again. The really basic form of this, by the way, the really basic form of this is simply taking a couple of really long wood screws. When you have that, that 6x6 or whatever it is, or 6x8 structural material, and taking two long wood screws and driving those two long wood screws at least 40%, if not 50% of the depth of that material, and then spacing the two screws apart the same distance apart as your invasive moisture meter pins. And then just using the heads of those screws as your contact point. So when you come back and measure, you just make contact with your electrodes right on the heads of those two seated screws. That's going to give you the wettest reading through the depth of that fastener, right? So that's the really simple form of doing this. But there are much more intricate ways of doing it. In many cases, I have actually used 8, 9, and 10-inch drill bits in order to get much deeper into structural assemblies, so I can range deeper into those materials and then use those left in place as opposed to the wood screws, just to give me that longer range depth, especially when you're dealing with a lot of very thick dimensional lumber. Okay, it can be very, very difficult. Even with a wood screw, it can be very difficult to reach 40% depth in some of those materials. But here's another little trick that I want to touch on that I love for crawl spaces. And again, my neck of the woods, I spent a lot of time dealing with crawl spaces. And this one, even though it takes a little bit of time to set up that first day, has saved me an infinite amount of time coming back to do my monitoring visits day 2, day 3, day 4, et cetera. And in this case, what I'm doing is I'm using just some speaker wire or similar and putting on ring terminals on the end of my speaker wire, as you can see here, 2 ring terminals, and then driving my screws, just like we talked about in the previous slide, through the ring terminals so that I can run the speaker wire out of the space, right? So that I can come back the following day and just use the end of that speaker wire to contact the area that's being monitored in the crawl space. Don't like spending a lot of time in crawl spaces, especially depending on the type of crawl space that it is and how what kind of clearance it has, what else is occupying the crawl space. So going down that first day and running in a couple of lengths of speaker wire and then bringing those back out with me as I exit the space, gives me a really easy way that next day just to touch a couple of wires and validate the same exact location, whether or not that location is making progress. I get a lot of questions on this, by the way, as to whether or not the length of the wire affects the reading. And honestly, I have not seen the length of that wire affect the reading. The resistance of wood is far greater, even at moisture content, is far greater than the resistance across some speaker wire. It's the lowest resistance that's going to set that resistance. And that's typically going to be the wood itself, not the length of that speaker wire. All right, so that would be another way in which we can monitor in these spaces effectively and kind of reduce the amount of time that we're spending doing our follow-up monitoring visits when we come back on subsequent days to investigate for progress. Okay, all right, so those are the monitoring methods. So last reminder here, make sure if you haven't dropped any questions into the Q&A that you do that for me now, because we're just about to hit that Q&A period. But as we do, let me review some of the important concepts here from Substructure Mastery. First of all, don't overlook them, right? Just like we talked about last month with interstitial cavities and voids, substructures are a critical part of the drying matrix, if you will. It's a critical area for inspection and investigation for drying, for validating that drying has occurred, especially with crawl spaces. It's really easy to overlook a crawl space, and it's really critical that we don't. It serves a very, very important purpose for that structure in that building. It is the foot, right? It is the base. It is the foundation of that structure. And if it's not dealt with properly, there can be some very significant long-term effects. Don't overlook them. Second thing is focus on the structure, right? We're not here to dry dirt. I don't believe that that you need to spend any more time drying that dirt, if you will, than is required to establish, safe and effective access for installing a new vapor barrier. So some drying of the dirt is going to be necessary, some pumping if you have standing water, removal of the existing vapor barrier and damaged insulation is very, very likely. But once you've gotten to the point where it's no longer muddy, install a fresh, clean, new vapor barrier in accordance with local code, right? And then finish drying the structure, focus on the structure. Don't forget the most important thing that I would share with you today about drying substructures is that 20-degree delta with dew point. I cannot hit that one hard enough to really drive home just how important this is, especially with substructures, because we're dealing with cooler surfaces, and it's really important to pay attention to this. And then last but not least, just a reminder from episode 8, use that formula, grain depression times CFM divided by 71 to evaluate the effectiveness of your drying system. Take credit for it, right? Use it in your documentation. Use it in your communication with property owners and property management companies or whomever else you're dealing with as a stakeholder for the reason that these systems are effective and the reason you know that they are effective within that drying environment, okay? So don't overlook them. Focus on the structure, 20-degree delta dew point, and grain depression times CFM divided by 71. So that wraps up the main part of our episode here on episode number 9. I'm going to go into Q&A here in just a moment, but before I do, let me give just a really quick commercial for what's coming up for the balance of the year. Again, my name is Brandon Burton, and I will be your host throughout this year for Technically Speaking. We have a couple more episodes that are coming up. Next episode on the docket is episode 10. If we only learn dew point first, would we even need grains per pound? And little probably prelude to the answer of that question is how much time I spent talking about grain or dew point temperature rather today. We're going to dig really deep into the world of dew point temperature on the next episode. And that's going to be October 25th, 10 a.m. Pacific, 12 Central. Again, episode 10. We're nearly wrapped up in 2022 for our episodes this year, and I'm going to start thinking about the episodes through 2023 here pretty shortly. So if you've got some thoughts on what should be in next year's Technically Speaking, please share those out with me. My email will be just a couple slides ahead. And if you missed any episodes, go to nextyearsolutions.com, go to Restoration Resources, and under Resources, go to Webinars, and you'll find all kinds of Technically Speaking episodes. You'll also find a number of other webinars that I have produced with IICRC's S500 update and other kind of just technical topics within industry outside of the Technically Speaking brand. So there's lots of webinars there that you can use for internal training with your group or just to stay current with what's going on in industry.